average Joe would do to you're hired as maybe this is one of your entry level positions here, and you need to predict. You're not an average Joe, you're a grad from Ottawa University, and your boss is telling you, I want you to predict what's going to happen in March. What would you do? You take the average. Okay, so if we took the average growth rate, what time periods would you pick? So let's just say that right now we're at 100, and here we're at 80, here we're at 50, and let's just do this. Here we're at 10, 20, 10. So, what rate of growth did you have planned? So from here to here, we have 100 minus 80 divided by 80 would be the growth rate. But from here to here, we had a smaller growth rate if we use those two numbers. I like your idea, by the way, because a lot of people, that would be kind of first blush thing, is kind of taking an average maybe. So what would be the appropriate one?
Some would argue to take the most recent one because it's the time.
Okay. So most recent is more important. Now we didn't put full, I mean, I kind of indicated, I guess, your months. So if we had 12 months, let's say this is 1 year's worth of data. So what's recent if this was a year's worth of data? 2 months, 3 months, 6 months, or is 1 year fairly recent? Yeah, so that, I mean, that's a good point. So this is what we call a naive forecast. So naive forecast is what Paige was kind of just pointing out. We're just kind of picking out where this line goes next. We don't really know we're not even attempting to explain what the underlying factors were that generated 50 in this time period, 80 in this time period, 90 here, right? We're not selecting that. So.
Like the way I look at it is that there was like swimsuits, and at the low point it's December.
Okay.
Washington, right? And then that higher number right now it's May going into June.
So we might have some seasonal
You know,
considerations.
seasonal, we have the tourist season, they were in Florida. The tourist season is economic factors like near Christmas time. You might sell more in hotter than the rest of the year.
Right. Okay. So if this was January, February, March, and we were trying to do this trend, would we want to maybe take the average of January, February, March a year ago? If that was an issue?
Yeah, I think you could. I know. And a lot of the like education that I was in this summer, we looked at the average for that like month or that like couple months for like maybe like a 5-year average, 10 or 25.
Okay. So
to kind of see where they thought like, okay, this is what it's done. Are we on the really high end of like what it's done? Are we in the really low end or in the middle? Like,
so were you computing like a moving average, or was it just an average of here's a 5 year, here's 1 year, here's a kind of went backwards, like here's a 2-month average, 6-month average, 1 year average? Is that what you mean? Except you were doing it in years?
Maybe it wasn't average. Maybe it was just like 1 day.
Okay, the actual. So a moving average is a technique that we're going to go over today too, where we take the 3-month average of January, February, March, and plot that point. So we were somewhere in here was the moving average. And then we do these 3 months, or actually just move up one. So the moving average here, and these months might have been here, and so it's a way to smooth out this line. Or it might go up and it might go down, kind of generally following that. And then you plot the move. You're always plotting the average of the last 3 months. So that's called the moving average. And it kind of helps to establish what the general trend was without just doing a straight line. Like most of the time when we've done this, we've done just kind of a straight line. And so that might be a helpful way to analyze the data. Any other considerations? Okay, so and some of that could be basically what you call a gut feeling added into forecasting. So when you're really at your new job and you're sitting in the boardroom, you might calculate this data and do a couple fancy averages and blow them away. You might even throw some regression we're going to show in it to show what that trend line is and where you think it might be. But then you might just say, well, remember we did that special advertising last month that our indicators show that that was going to be a positive thing, and maybe that'll bump up the number by X amount, or we didn't do it this year, even though last year we hired LeBron James to do it. This year we could only afford Britney Spears. And so, does that factor in? So it's literally part of the forecasting could be having some of these basic models. This is what is easiest for the boss to grab onto, using averages or moving averages and trend lines. It is still kind of surprising sometimes how easily odd people can be by just doing some really simple things like with moving average. And if you do a regression line, which by the way is cookbook in Excel, as we've been really running regressions, but if you do a graph of some data, and I think we do this maybe in the other exercises, but you literally can just say regress between these data points and these data points. And then you just press the button regression. So you're not doing what you guys have been doing, you're really running a full regression with new data. It's not multivariate, so it would just be a simple two variables, whether it's time or two variables graph, and then you just literally press the button regression and it'll show the regression line. So that's pre-built into Excel for some of your diagrams and plots. So, and then it kicks out, I think, the R-squared and the regression coefficients. That'll show you the slope-intercept form of that regression line. And Excel just does that automatically. And so if you want to blow away your future bosses, you can just throw a little regression. The catch is you guys got to know what the heck you're talking about, because they will be impressed, and if they're smart, they might ask a question, but they might pretend like they know what you're doing, and you just go, oh yeah, that's good analysis. But the reason you guys are in class is that you actually kind of know what you're doing, right? So you could explain the R-squared representing the amount of variation that variable is picking up in the regression. So, okay, I wanted to show you a naive forecast that I did with my buddy from graduate school. We worked on this project just a couple of years ago. I presented it at a conference, and we attempted to get it published, but it did not get accepted at the journal that we did, and then we're like, screw it, who cares? That's mostly done with anything. So we didn't really fuss with it much more. But, so who works in admissions? Paige, you the only one? Okay. So you might get more out of this than the other, but I mean, in terms of having just insider information. So at the time I was just giving some descriptions about the number of students, the number of undergrads, a little bit of our university. And then, this was 2016. And so looking at applicants with paid deposits. You guys remember when you put down your deposit, right? So we're going to use that as the thing that means you're probably really coming. So we always have a few defectors at the end, but for the most part, if you put down a deposit, it's a pretty good signal that you're going to actually come in August, regardless of when you put the deposit down. Put it down in January or April or June or whatever. So the data that I got from our admissions team was just the number of applicants. So they kept an Excel spreadsheet like this, and we took the number of applicants that we got as we moved through time. So there's 52 weeks starting from September 1st, of course, for 1 full year. And the data over time was these are 5 years worth of data, I think it was. So these gray lines are how our admissions looks over a 5-year period. And you can see it kind of follows a similar path, right? Just a little bit, we get into an area and it kind of turns. So, and by the way, this is all my buddy's work. He was the econometric freak of nature, and so he was doing this at his school, and then I can't remember how this came up, but I asked him, somehow we got to doing this for Ottawa. So he did this for his, he's the one that kind of saw this pattern. But what was interesting is we saw a similar pattern for Ottawa that we did at University of Central Missouri. So a lot bigger school, state school, completely different, but they had a similar pattern that they have for their enrollment. So we got weeks going on here, and then total deposits. So the model was a third-degree polynomial. So this mathematical function going up to the third degree gives you those 2 turning points, right? So back in when you're taking your old math class, you're graphing out equations, right? That allows that turning point, those 2 turning points. And so then we just put that into a regression to see if we could estimate these parameters on each one of those W's. Each one of those are basically t, it's time, right? So at week 52, or at week 36, then it's 36 squared, 36 cubed, 36, right? That's all it is. So it's a naive regression in that we're not taking into account how many high schools we visited and other recruiting activities we did. We're just merely observing the pattern of where we're at today versus where we hopefully want to be tomorrow. So this was using a different computer program to do the regression, but these are your estimates and your t-values. So we've got the coefficients greater than 2, so same type of stuff going on with the regression, that these were significant. And again, it's just timing being significant, but it really is speaking to the fit of the function compared to the data. R squared was not real high, 0.47, so 40% of the 37% of variation being covered. But this is where it was interesting. So the standard error of the regression was 2.6. So the interpretation of that is the 95% confidence interval is where you are 2 standard deviations away from the mean. So with this coming out at 2.6, we are within 10 students of where we should be for June, depending on when we ran it. And this was in week, I think this was week 36 or something. Maybe the next one talks about that. So we're predicting in April where we're going to be in the fall. It's pretty useful for they're always trying to figure out how many people we're going to have in the fall. And so this is where we max out in week 30, is approximately where our deposits start to fall off. And so this is per week. Weekly expected deposits, 2, 4, 6. So here we're not aggregating them like we were before. The total number of deposits is going up and down. All right. I think I'll skip the rest of this here. So this was on April 11th and 6-4. So on April 11th, the model predicted 262 students back then. So the red line is the math taking over from where we were at. The blue line is the actual deposits collected up to that point this year. And then the red line is the 262. And then as we get more information, we get a tighter estimate. And so here it was 263. Okay, questions on that? I'm not meaning for this to be all inclusive, just kind of want to show you some of the ways we can use this. So, for fall 2015, week 39, ending June 4, we have 203 deposits, and at the same time, 1 year ago, we had 214, and the 5-year average at this point of the recruitment cycle was 188. So, they're usually left saying, well, how many people do you think we're going to get? Well, this year we were at this time, and this is the average, so that's why we're doing kind of some of the summary data of where it is. And my buddy had the computer program was cranking this out. And so the prediction was 263. Previous fall had 268. And this is where we ended up. The actual total fall was 292. We had 29 fall out. We actually got 263. Bingo! Right on the nose. That doesn't happen very often. we got lucky with that. Okay, so anyway, that is the idea, part of the idea of forecasting. And to my surprise, it just never really. It's funny. I didn't want to intervene too much, but I would pass the reports along. And I never really got much feedback. So I don't know if the enrollment department really gave it. So that's what was kind of interesting. Even though it was a pretty good predictor. I think by the time you get busy with other things and think the latest, greatest thing, next thing moving out. But it does take time and effort to analyze that. I mean, everybody up there is so wrapped up in whatever they're doing. That's where you kind of need an outside either consultant or somebody else that's thinking about this type of thing. But what we're showing is that if you really care about where we're going to end up in the fall, this might be a decent approach to keep in mind. Okay, so open up your books next, or if you don't have your book, you can, I'm going to put it on the screen. Hey, are you the only one with that one? Otherwise, if you want to brought back with Chisholm or something, but the screen should work just fine too, so it doesn't matter. Oh, by the way, that pattern is the Gophers curve, which is also covered in the book here. So that was for a different type of problem, but that's something that's discussed a little bit later. All right, so I want you to turn to time series analysis. So page 142. Do you guys got the international version? Is it the same? Somebody does. Chisholm, is that you?
I do.
Okay. All right. So I'm going to do a little round robin reading with this. So I'll start off with this section, and then let's just go, Alex, and kind of just round robin. Take about roughly a paragraph or so, see where you end up. Doesn't have to be super formal, but I want to kind of read through this word for word. So in this section, we'll continue exploring time series forecasting. So up to this point, by the way, they went through some of the stuff I just talked about with different ways to do averages. And so this chapter really starts on page 132, is the forecasting section. And so they talk about some of the stuff I just did. However, instead of a visual estimation, a more precise statistical technique will be employed, the method of least squares. This method was introduced earlier in this chapter and was used to estimate demand. Whereas demand estimation requires the use of one or more independent variables, and the interactive relationship between these variables is of great importance. In this context of time series analysis, there is only one independent variable, time. Thus, the system of forecasting is naive because it does not explain for the reasons for the changes. It merely says that the series of numbers to be projected changes as a function of time. All right, so Alex, why don't you continue on?
Despite the mechanical nature of this type of forecast, time series analysis has much to recommend it. One, it is easy to calculate. A large number of software packages is available. Two, it does not require much judgment or analytical skill by the analyst. Three, it describes a line with best possible fit and provides information regarding statistical errors and statistical significance. Four, it is usually reasonably reliable in the short run, unless an absolute turn in the series occurs.
So let me pause there for a second, because that's kind of what we did here. Usually when you do these types of forecasts, naive forecasts, you want to be pretty short term in terms of how far you're projecting out. You're not doing a 5-year run or whatever usually. I mean, you might use it that way, using the moving average or something, but you better have some pretty good reasons. So if you're really trying to predict, you're usually kind of short time frame out. Okay. Zach, why don't you go ahead?
Okay. The fact that time series analysis does not take into consideration positive factors does not mean that an analyst using this method should not consider additional information about changes in underlying forces. Any analyst using this naive method of prediction should try to find conclusions based on information that can alter the results.
When data are collected over a number of periods in the past, they usually exhibit 4 different characteristics. 1, trend. This is the direction of movement of the data over a relatively long period of time, either upward or downward. 2, cyclical fluctuations. These are deviations from the trend due to general economic conditions. For instance, if one were to observe data for the GDP over time, a long-run upward trend would be evident. Also evident in this series would be movement around that trend as the economy rises more quickly or less quickly, or actually declines. 3, seasonal fluctuations. A pattern that repeats annually is characteristic of many products. Toy sales tend to rise briefly before Christmas. Fashions have spring and fall seasons. In the soft drink industry, the expectation is for higher sales during the warmer periods of the year, i.e. June through September. Thus, time series in which data are collected more frequently than annually, monthly, or quarterly can exhibit seasonal variations. 4, irregular. Departures from norm may be caused by special events or may just represent noise in the series. They occur randomly and thus cannot be predicted.
All right, I'll take over this little spot here. How to read some of that stuff. So time series can be represented with this math expression, which is just your trend, cyclical, seasonal, random components. We're kind of thinking this variable is dependent upon those 4 components, right? And then we're going to dissect them. You can do different functional forms. You can do an additive form or a multiplicative form. And the most commonly used is the multiplicative form. All right, so Paige, why don't you just take from there?
Most of the changes in the actual values are determined by 4 factors. Half of the analysis is the time series of y into its 4 components. Now return a big problem called forecasting cycle name field. For the entire year 2015 for each quarter. Prior procedure is summarized in table 5.5. The alternative method of obtaining seasonal
Indices.
using regression analysis is examined in seasonality and seasonal indices Excel app.
Okay, let me take it from here. So the process of decomposition starts with identifying and removing the seasonal factor from our series of numbers in order to calculate the trend. We use the method of moving averages to isolate seasonal fluctuations. So column 1, I'll show that in a second here. This column simply represents all of the quarters of the 11 years, 2002 through 2012, numbered sequentially. So the data set off to the left here, we've got quarters, right? So 1 quarter, 2 quarter, 3 quarters, so 4 quarters to a year. And then we have the actual amount of the citronade sales. So that's in dollars. So then the moving average is our first step. So column 2, all the quarterly data is organized there. The first step in deseasonalizing process, Paige, why don't you read this?
All three?
Yep.
The first step in the seasonalizing process is selected a quarterly average for first year, i.e. the first 3 quarters. Result is 173. Number is placed next to quarter 3 in this column. Next number is obtained by moving down from the quarter. The first quarter is dropped, the fifth quarter is added in, the average of quarters 2, 3, 4, and 5 is calculated to be 989.3. This number is placed next to quarter 4. The same procedure is then followed with the rest of the quarters. This is the averaging in the data for the first 2 quarters and last quarter are lost. Therefore, the average is placed next to the third quarter. It can also be placed next to the second quarter. Actually, the average of 4 quarters belongs between the second and third quarter. This composition is made in column 4.
Okay.
Computation.
So, back to the data. Now, we got a lot of stuff going on here, right? So, we've got 4 quarters to a year. So, if we take this one plus this one plus this one plus this one, divided by 4, we get 973. So, the centered moving average is that, well, that's not quite fair, because that's not really the number at that spot. So we're going to, with column 4, an average of the 2 adjacent numbers in column 3 is calculated and placed at the third quarter, because 973 in column 3 should have appeared between quarters 2 and 3. And 989 should have been between quarters 3 and 4. The average of these two, 981, is correctly placed at quarter 3. All centered moving averages are placed in column 4. With this procedure, the next to the last number is now lost. Everybody tracking with that? I like to go through this one slowly. So, everybody cool with 973? To get 973? The first 4.
Okay.
So that is 1 year's. This is the annual average.
So what about
973 is the annual average, but it's really at 2.5 quarters. So the next average is 1, 2, 3, 4. Right? So it's a moving average is 989. And then the next quarter is 1, 2, 3, 4, average of 1,000. Okay? So now, what we want to do is bump that up to the right quarter. Now we have the moving average here, but to center it on the right spot so that it's really on quarter 3, we're going to take the average of 973 and 989, and now we are right on quarter 3. But to do that, we lose the last observation. Because we're taking the 1, 2, 3, we don't have the third to grab onto. And that was with the moving average. Remember, it was 1, 2, 3, 4 was the annual, which is here. And so we don't have this data point to do this one, so we lose it. And then the same thing goes on here when we're doing the averages at the bottom. We're going to lose that last one because we don't have it. Put it there. Okay?
Oh, so like,
Yeah.
So like the 981 in column 4, is that just the 973 and the 989 added together and divided by 2?
Yep.
Okay.
Yep. So over around here, an average of the 2 adjacent numbers in column 3 is calculated and placed at the third quarter because 973 in column 3 should have appeared between 2 and 3. 989 should have been between the other 2, so taking the average of 2 puts us right on 3. Right? So this one really belonged at 2.5, and this one belonged at 3.5. So 2.5 plus 3.5 divided by 2 puts us right on 3. So now 981 is centered on that quarter. All right.
What does centered moving average represent?
The actual moving average is, we just kind of put it in here because we didn't want to create a 2.5, if you want to think about it that way. So we kind of incorrectly, in a sense, put it here. What if we wanted to bother with it, we would have did 1, 1.5, 2, 2.5, 3, 3.5, 4. Then we would have shifted all these up by a half of an increment. And then now what we're doing is that just puts this one right in line with the third quarter. So because we're really trying to pick out the timing of the data, and so we want to make sure that this going back to the actual data, in quarter number 3, we actually sold 1,236, right? And that's the actual amount for quarter 3. And another thing, kind of centering, if you want to think of it this way, 1, 2, 3, 4. So what do we have? We had 842 and 939. 842 and 939. 1, 2, 0. To center this up for graphing purposes, sometimes we put this here, the data point, because it's kind of over quarter number 1, we got 842. So sometimes when we graph things, we did that also. But now, since we want to keep this straight, the data was collected and gathered here at the end of quarter 1, so we're going to keep that straight. So then the average of the two is all we're doing with the centric moving average, is lining that up. Okay. Alex, number 5.
We now obtain the seasonal factors. They are the ratios obtained by dividing the actual numbers in column 2 by the center moving averages in column 4. Observing the numbers in column 5, it can be seen that every fourth quarter, starting with quarter 3, 7, 11, and so on, has a factor greater than 1. These quarters represent the summer months, July to September, when soda consumption is at its peak. It can also be seen that the data for the second calendar quarters, in quarters 6, 10, 14, and so on, are rather close to 1, whereas the quarters representing fall and winter are generally below 0.9.
Okay, so column 5 takes the data and looks at the ratio of when are we high, when are we low, right? It's a straight ratio of actual versus the moving average. How are we doing relative to the trend? Are we above trend or are we below trend? Right, so our trend line is the black. Are we above or are we below? That's all we've done is create a short little ratio. Good with that? Zach? Column 6.
To obtain a quarterly seasonal index, we must average the ratios obtained by quarter in column 5. This is on table 5.6. Quarterly patterns are quite obvious. 4 averages should add to 4. They do not either rounding. A minor adjustment now must be made. The results are then transferred to column 6 on table 5.
Okay. So adjusted seasonal factors. Oops. So to obtain a quarterly seasonal index, we must average the ratios obtained by quarter 5. So we're doing an average of many averages now, right? So we're now going to average those as we move through time. So then we start to see the ups and the downs of the seasons. Now seasons here are not fall, winter, spring, right? The seasons are the busy selling season of the whatever the summer's going on for my particular business. So the seasons are seasons of your business whenever the stuff gets hot to try. Okay, 7. Chisholm?
When the actual data of column 2 are divided by the seasonal factors of column 6, the deseasonalized series numbers in column 7 are both the actual and the deseasonalized data have been plotted in figure 5.6. The latter series should be expected is much younger than.
Okay. So column 7, we're going to factor in the data and take the seasonal factor out of it. So now what's interesting here is we're actually filtering it out, that seasonal effect, to say, are we really high for this season or are we not, right? We factored that into account. So where was the picture again? 5, 6. So here's the actual data, and here is it with the seasonal factor out of there. So you really start to get the trend line of what's happening, filtering out the Christmas effect or the hot weather effect to get that actual trend. Let's see, we're about out of time, I guess. Yeah, so that's about, so then 8 and 9, I'll let you guys kind of read on your own. And it kind of brings you into this next table as well. So that one I just wanted to get you guys started on. I think you'll pick up the rest of it pretty easily, but it's, I think, kind of helpful to work through that table slowly as to what's really interesting at that particular table. I can't say I did a bunch of that stuff with my econometric work that I was looking at, so.